Hello everyone. Today let's explore the real-world applications of differential equations. And friends, by the end of this video, you'll have a good idea of the immense contribution of differential equations in our present world. So let's start. An important application is the population model. So friends, whether it's the growth of human population or the number of predator versus prey or the growth of microorganisms, we have population which is constantly changing with respect to time, and this can be very well depicted using differential equations. And one such model is the logistic population growth model. If P is the population and T is the time, then the rate of change of P with respect to T is directly proportional to the product of P and the difference between the carrying capacity and P. So friends, what is the carrying capacity? It is nothing but the maximum sustainable population. So friends, on solving this differential equation, we get this expression using which you can find out the population for any given value of time. Here is another model, the SEIR model, that is being currently used to analyze the COVID pandemic. Friends, S stands for susceptible, that is, those people who are at risk of getting the infection, and ds by dt is given by this differential equation. Friends, did you see that beta is the transmission rate of the virus? Now, from these susceptible people, you have some people who will be exposed to the virus, and that is denoted by E. So dE by dt is given by this differential equation, and sigma is the infection rate. Now, some of these exposed people will actually get infected with the virus, and that stands for I. So here is the differential equation that shows you di by dt, and sigma is the recovery rate. Now, last but not the least, you have R, that is removed, that is those infected people who either died or got completely recovered, and this is the differential equation for dr by dt. So friends, this only underlines how invaluable this data is for all those people who are currently fighting with the pandemic. So differential equations undoubtedly is very valuable for population models. Friends, did you know that differential equations is very useful in the world of music? Let's see how. So here is music from the piano, and this is from a synthesizer playing the flute sound. So why does a piano and a flute sound different, although they are actually playing the same set of notes? Well, this and many more such questions are being analyzed thanks to differential equations. This is the differential equation that's used for all musical acoustics. So friends, as you can see, this is a second order and partial differential equation. So why are we using differential equations over here? Because we are dealing with sound waves whose shapes are constantly changing with respect to time, and hence we can use differential equations to model their behavior. Now friends, this differential equation describes sound variations, and solving this will help us understand why some notes when played together sound very pleasing, something like this, while others don't, like this. The next application is Newton's law of cooling. So friends, this law states that the loss of heat from a body is directly proportional to the difference in the temperature of the body and that of its surrounding. So you have temperature of the body that is changing with respect to time. So that means we can use differential equations to describe this law. On solving this differential equation, we will get a relation between the temperature of the object, the temperature of the surrounding, and the time t. So friends, you can find the temperature of the object at any given point of time. Now friends, this law is being used widely in the packaging industry, where food is subject to high temperature treatment and then it has to be cooled for packaging purposes. Now let's see how this law works for an ice cream. The temperature of an ice cream when taken out of the freezer, supposing, is minus 20 degrees Celsius and the outside temperature is 30 degrees Celsius. Now, after 1 minute, it's been noted that the ice cream temperature has increased to minus 10 degrees Celsius. You need to find out what is the temperature of the ice cream after 5 minutes. Surely it has increased, but you can find out by how much using Newton's law of cooling. By doing these calculations, and friends, you'll come to know that the ice cream temperature after 5 minutes is 15.61 degrees Celsius, which means the ice cream is going to literally melt in your hands. Differential equations are very useful in radioactive decay. Let's see how. So friends, radioactive elements like uranium, radium, cobalt, etc. on being unstable spontaneously decay to give the daughter nucleus and the alpha, beta or gamma rays depending on the type of decay. So we have a law of radioactive decay which states that the amount of the radioactive element that is decaying per unit time is actually directly proportional to the total amount of the radioactive element present. So since the quantity of the element is changing with respect to time, we can use differential equations to express this law. And friends, please note the negative sign indicates that the quantity of the element is actually decreasing as time progresses. On solving this differential equation, we will get the relation between the quantity of the element and time t. So you can find out how much quantity of the element is remaining at any given point of time. One use of this equation is to find the half-life of radioactive elements, which is nothing but the time that is required for half of the atoms in the sample to decay. So here we have cobalt, which is a radioactive element, and friends, its half-life can be found out to be 5.27 years using appropriate values in the equation. This half-life value is of great importance, friends, because it tells us how much quantity of the radioactive element is actually present as time progresses. And as you can see in this graph, the percentage of cobalt 60 that is remaining as time progresses is exponentially decreasing, which means cobalt, which is widely used for cancer treatment, has to be replaced regularly in order to be effective. And for this, differential equations is very useful. The next application is an economic analysis which includes GDP calculation. Friends, the change in GDP with respect to time is found to be directly proportional to the current GDP of the economy. So if X is the GDP of the economy, here is the differential equation that comes into the picture. G is the growth rate, and on solving this differential equation, we'll get a relation using which you can find the GDP for any given point of time. Differential equations come very handy in macroeconomics, which is nothing but the study of large economic systems like that of a country. So one such equation, friends, is the Fokker-Planck equation, which is a partial differential equation describing time evolution. So friends, equations like this help us understand why some countries are poorer than others, what causes recession, and how to deal with them. The next application is Maxwell's equations. Friends, this is a set of 4 coupled partial differential equations that describe how electric and magnetic fields are generated and altered. So the first law is the Gauss's law of electric field. The second law is the Gauss's magnetism law. The third law is the Faraday's law of induction, while the fourth law is the Ampere's law. So this triangle symbol that you see is the del operator that is used for divergence and curl vector operations. So these are 4 complex laws, but they are the building blocks for all types of electrical, optical, magnetic technologies and innovations such as smartphones, mobile phones and computer technology, making MRI scanners in hospitals, electric motors and generators, and also to better understand the various phenomena of light. The last application we will be discussing is the Newton's second law of motion. So friends, this law states that the rate of change of momentum of an object is directly proportional to the force that is applied on it. So since momentum is changing with respect to time, that means we can use differential equations. Friends, there are two scenarios to this. If we assume the mass of the object to be constant, then we get the well-known formula that force is mass into acceleration. However, if the mass is variable, that is either it's increasing or decreasing with respect to time, here is the differential equation that we will be using. The variable mass equation is very useful to study the motion of rockets because the mass of a rocket is decreasing with time as fuel is burnt and propellants are being expelled. But let's take a simpler example of pushing a shopping cart. So friends, if the shopping cart is empty, we have all experienced that it's going to take less force to push it because the shopping cart has less mass. So less mass, less force needed. However, if the same shopping cart was filled with, say, gifts, although you would be delighted to push them home, it's definitely going to take more force to push it because now the shopping cart has more mass. So more mass, more force needed to push the cart. So friends, thanks for watching and I hope you found the video useful. If so, do like and share the video. Please leave your comments in the comment section below and do consider subscribing to enjoy math. So till we meet again, take care. Bye.